All right, everybody, welcome back to ECE-T480, Operating Systems Design. I'm Dr. Shackleford, and today we're going to continue talking about memory allocators. And so, where we left off on Monday, we were talking about the idea of page frame allocation, this thing called the binary buddy allocator that sits there and it grabs, big blocks of physically contiguous memory in orders of 2, right? So you can get 1 page, or you can get, which is 2 to the 0 pages, right? Order 0, or you get order 1, which would be 2 to the 1 pages, so 2 pages, or order 2, which would be 2 to the 2 pages, so 4 pages. And, at the lowest level of the memory allocation system, this is pretty good, right? So the system can, request, either for kernel space usage or, for user space usage, if the kernel is being asked to map some number of pages into the user space, this is helpful. We can get reasonably sized chunks of physical memory that we can map to the various regions of the virtual address space, whether that be, the kernel space over here, that lives somewhere in the top of memory, or the user space that lives underneath it somewhere. And so this is pretty good stuff, right? But, we talked about how there are some issues, right? There's some issues with that, right? What if we want smaller allocations? And if you remember, we looked at this problem. We said, hey, the binary buddy allocator has a problem because in kernel space in particular, right? If the kernel says I need to dynamically allocate 300 bytes, just 300 bytes, then, if you just talk to the buddy allocator directly, it's going to say, well, hey, the least I can give you is order 0, which is an entire page, right? And on a lot of systems, that's 4 kilobytes. On other systems, it could be 8 kilobytes, which is even worse, right? And so then the kernel would, put its sad little amount of data, it's 300 bytes, into this huge page that's mostly going to go unused, right? And we would have this problem of internal fragmentation, right? Where, you have these memory allocations, right, where large amounts of them internally are not being used. So if you were to look at all of the page frames, right, and see what their usage looked like, you'd see all of these gaps, you'd see all these unused spaces in the page frames, right? Because we would be allocating more memory than we needed. We said, well, this is a problem, right? We looked at how, as these allocations become bigger and bigger, this becomes more and more wasteful, right? This becomes more and more wasteful, right? Because if we go 1 byte, if we say I need 4,097 bytes, right, then we get 2 page frames, right? And one of those 2 page frames we would only be using 1 byte of, so it would be nearly completely wasted. And so, I introduced the idea of how to fix this. I said, well, there's this thing called the Slab Allocator, the Slab Allocator. And what this thing does is it packs commonly allocated objects into blocks. And that's the thing that you need to recognize about the kernel, right? Is that the kernel, has a certain number of jobs, right? It doesn't, it does a fixed number of things, right? It manages files, it manages network packets, it manages processes. It's not doing crazy off-the-wall stuff, right? It knows, the number of data structures that it needs, in other words, to support the small set of things that it's responsible for. Are known, and they're commonly allocated, right? And so, if you look at your system at any given time, which we'll do in a little bit, and say, hey, how many, data structures are there on my system for processes at the moment? Or how many data structures are there on my system that represent files at the moment, right? This is the idea, right? The kernel is allocating, the same type of struct many times. Like anytime a directory, is created, there's going to be a type of struct for that when the kernel's keeping track of it, right? Whenever a file is opened, the kernel's going to create another, file pointer struct, right, in order to keep track of that. And so, or file descriptor struct, right, to keep track of that. And so the kernel knows, right, it's got a set of data structures that it creates all the time whenever a certain hardware or logical resource is in use. And, since we know the sizes of those things, right, in advance, like we know how big a network packet is, we know how big a file descriptor is, we can divide up these pages into what are called slabs, right? We can take 1 page or we can take multiple pages, ask the frame allocator, right, for some order of pages, either 1 page or 2 pages or 4 pages or whatever, and then we can divide that page up to contain, pre-allocations basically for these data structures that we're going to use. We can pack them all in there real nicely. So let's see how this looks, right? Let's give you an example of how to use this thing, right? So that you have something to hold on to, and then we'll see how it works. So let's say that this is your kernel module, right? And let's say that you have some data structure called a thing. It's a struct thing, right? It's some sort of K object, right? You are going to use this to represent something on the system, and it's got some values that you care about. We're just going to say it's called val, right? And let's say that your kernel module is going to allocate a lot of these things, right? Like as devices come and go, you might allocate a struct thing, and then you might release a struct thing, and then a couple more hardware devices might get added, and you'll have to allocate a struct thing to represent each one of them. And then once those hardware devices go away, you'll have to release them. And so not only can this get expensive, right, in terms of memory, if you're doing allocation like this, right? If your struct thing takes up this much space, right, and the whole page is this, like we don't want this, right? So we want to be able to pack these things, multiple struct things, into one of these pages, right? And so that's what the slab allocator does. Right? And it also makes allocating these things fast, as you'll see. So let's see how this goes, right? What you do is you set up this thing called Slab Cache, right? And so let's see how this goes, right? What you do is you create a structure, right? I'm sorry, a pointer to a structure of type kmemcache, right? This is going to give you a pointer to a memory cache, right? Which is basically, and we'll look at this in a lot of detail in just a minute, but it's basically a store of pages like this, page frames like this, that you're going to use to store, your little struct in, right? You're going to pack them in there, right? So that's what a memcache is, or a slab cache, right? The API calls it a kernel memcache. In reality, it's a slab cache, and we'll see how that works in just a bit. So you're going to create one. And so, it's going to have an address after you create it. And so you need a pointer to keep track of it, right? And what you'll do is you'll call this fancy macro. And like I said, kernel developers love their macros, right? Especially when it comes to object creation to prevent people from messing it up. So you call this macro here, kmemcache, and you supply the name of your struct, right? Just the tag. You just put the tag in there. This is the tag of the struct, right? It's just thing. You don't write struct thing in here. You just write thing, which is a little weird, but we'll see why in a minute. And then you have this 0 here, and this 0 is the flags. These are the kmemcache flags. And this is going to talk about, hey, where do these pages come from that we ask the binary buddy allocator for? Should they live? Should these slabs or these chunks of memory that we're going to be packing our objects into, live in physical memory that we can do DMA on? Right? Do we need to use these blocks of memory that we're going to allocate using this cache to communicate to hardware devices, or like legacy, like old hardware devices, or maybe somewhat newer hardware devices that can do 32-bit DMA, right? Should we panic if the memcache fails, or can we handle it gracefully, right? And how do we should this allocator try to align our objects to cache lines, right, for optimization at the expense of storage efficiency, right? So these are the sort of flags that you have. And, at this point, you're not going to need any of them. I do want you to know that they exist. You're not going to be writing a kernel module or a piece of kernel code that would cause, that would be unrecoverable if the allocation failed, right? In the worst case, at this point, you might just print something to the kernel log that said, hey, I couldn't allocate the memory, this module can't be loaded. Or, oh, hey, I couldn't load some memory, this device driver can't be loaded. But if you're somewhere deep in the kernel, right, and you absolutely have to be able to create this cache to allocate your objects from, like let's say, structures that represent a process, then obviously you would panic and bad things, would happen. You would alarm the user through the kernel log and not continue the system. Right, so these are the sort of flags that exist. I just want you to know about them. And so this macro here expands into something, obviously, and I'll show you what it is. So you put the name of the struct, the tag of this struct here, because this macro does stringification on it, right? And if your C macros are strong, you'll know that you can use the hash symbol within a macro to stringify something, right? And so this will take that tag that you provided here, and turn it into a string literal that it passes in as the first parameter to this fancy function called kmcache create. So we're creating a slab cache, and we'll see how slab caches work in just a bit. It then also, expands into this. It gets the size of the struct that you passed in, it writes size of struct, and it just fills in thing here from where you supplied, the tag of the struct to the macro, right? So it knows the size of the objects that we're going to be packing in to these pages. This is a compiler built in that you can use to get the alignment of an object, right? And if you've ever looked at this, if you look at the pointer of a byte, I'm sorry, if you look at the pointer of a float or the pointer of a int or a char, whatever, not a char, but of any multi-byte data type that you've allocated in the past, you might notice that it's always like a multiple of 0 or a multiple, the address, right, is always like a multiple of 0 or a multiple of 4 or a multiple of 8. And that's because the CPU has alignment requirements when you're fetching multi-byte data types. If the multi-byte data type doesn't fall on the proper byte alignment boundary, in other words, its address is not a multiple of 4 or 8 or whatever is required by the architecture, then when you try to fetch those multiple bytes for that single value, the processor will fault, and you'll get stuck in some sort of exception, and then the operating system has to handle it and basically take the slow path to fetch the rest of the bytes for that single multi-byte data type. And so to keep things fast, we try to comply with the architecture's requirements for multi-byte data type alignments. And that's what this is. The compiler does this for you automatically when you allocate things on the stack, right? But when you're allocating things dynamically at runtime, you have to do it yourself. And so this is what you're doing, is you're telling the memory allocator at runtime what the alignment is of this thing that you want to allocate, so that every time it allocates a struct thing for you in one of these blocks, right, one of these pages, it knows what the what multiple of an address, right, or what multiple of basically what the byte boundary, right, should this thing be allocated on a multiple of 4 or a multiple of 8, or what are the requirements for the address alignment of this object. And then of course our flags just get passed directly through. And this last thing is fancy. The macro assumes that you don't want this. If you're using the macro, then you probably don't even know about this because it's hidden from you, but you can actually supply constructors for these things. So when you ask later to allocate an object from this cache, from this block, from this page, to get a struct thing, you can actually tell the slab allocator to initialize it for you in some way. And this is where you would pass a function pointer. And that function would be called automatically and initialize the object for you before it was returned to you. So this is rather nice. And so what this does, again, if you call kmemcache, this is the easy way to do it, right? You supply the tag of the struct, which is the thing you want to allocate, you put in your flags. And what this thing will do is this will create a memcache for you called thing, right? The reason that this gets stringified like this is so that there is a user space visible way of identifying this cache, this slab cache. And as you'll see in a little bit, you can query this from user space. It exposes itself, as you might imagine, as a file, right, that you can read, and you can get a big list of all of the memcaches, right, of all of the slab caches on your system, and see, how many, of each of the objects exist and all this great stuff, right? So this is just a way for us to identify this from user space. It has a name, and it has the name of whatever the struct is. And so we just created a thing cache, right? So this is what will happen is the slab allocator will allocate a slab of memory, right? This slab could be 1 page, could be order 0, or it could be 2 pages, right? It could be order 1, or it could be 4 pages. It could be order 2. The slab cache is smart about this, right? It makes a guess on how big an individual slab should be based on the size of the objects that it's going to try to pack in there, right? And so these objects are pretty small, right? Struct things are pretty small. And so let's just assume that it's going to be 1 page, right? So this is our slab. This is our slab. And what's going to happen now is when you want to allocate a struct thing, you're going to call kmemcache alloc, right? And you'll pass in for the first parameter the address of your slab cache that you just created, right? The address of, kind of this thing here, kinda, right? Kinda, we'll see how that works in a minute, right? And then you'll give it the same sort of, get free pages flag that you would pass to kmalloc. You say, hey, you know, is this just a general kernel allocation? In other words, can this thing sleep? Is it safe to sleep? If it's not safe to sleep when we're trying to allocate this block of memory for foo here in this slab cache, or in this slab, you know, we would put GFP atomic in here. In other words, you know, this is happening in an atomic context, right? Don't go to sleep. That would be really bad. Like if we were holding a spin lock, for example, right? And so this is basically how it works, right? You create a memcache, right? You tell the slab allocator, you know, what the name of the memcache should be, you know, what type of structs it's going to be allocating in there, you know, any particular physical memory requirements that should be placed on that. Should this memory be DMA-able or not? And then you'll get the address of a slab cache. And then you can use that slab cache like we are using here just to allocate objects. And the only type of object that you can allocate from the slab cache is a struct thing, right? So anytime you call kmemcache alloc, you know, and you pass in, you know, this specific cache here that you just created, that's a cache of things, you'll be creating a new struct thing. This one's called foo, right? Save its pointer here. And this one's called bar, right? We put its pointer here. And now we can use these just like we would use, you know, pointers that we would get back from kmalloc. But look at how nicely they're packed into memory, right? Remember, what this macro did is it also passed in the alignment. In other words, you know, what multiple, what byte boundary, what address boundary do these objects need to live on? And so, you know, that's why they look like this. Your actual data is in here, but the allocator also inserts this pad, which is just, you know, garbage data. It's nothing, right? Just to space this out to make sure that the beginning of the next one meets the alignment requirements. It starts on an address of the appropriate multiple, right? Either an address that ends in 4 or an address that ends in 8 or 0 or whatever, right? So this is to satisfy the architecture. And so you can see, you know, how this solves our problem. Right now, you know, we won't have that internal fragmentation issue. Every time we want to get a new struct thing, you know, it'll just kind of be placed in this slab, right? And this is really great. Likewise, when you're finished with one of these struct things, you know, you just call kmemcache free and you pass the address of your memcache and the address of the thing you want to free. So it kind of works like kmalloc again, right? And so these things would be freed. And obviously, you know, when your module unloads or whenever you're done with it, you would destroy the memcache. You would destroy the memcache because this thing's registered with the slab allocator, this cache is, right? So just because you unload your module, it doesn't just magically go away, right? Like it's registered with the slab allocator. So you have to tell the slab allocator, hey, you know, my module's going to go away. You don't need to keep track of slabs of this size anymore. You can safely destroy this. You don't have to manage it anymore. So hopefully this is fairly straightforward. And of course, you have to include slab.h if you want to work with the slab allocator. Now, you know, you can also do things like OR some special free page flags in here. This is a bitwise OR. You're just ORing a bit or flipping a bit in this flags mask that you're passing to this alloc request. If you OR in, you know, underscore, you know, the double underscore things are generally like, you know, advanced things, right? They're generally wrapped by something else, you know, but you can call them directly if you want, but this is an indicator that you're doing something that, you know, is generally hidden under at least one layer of user API, right? But, you know, you can absolutely do this. You can, or, you know, the general, you know, hey, I just want a regular kernel, you know, allocation. You can go to sleep when you do this allocation. It's fine. You know, just give me some memory. You can OR this with GFP0, and this will initialize the blocks of memory returned by the slab allocator to 0. And so this is great. This will automatically zero out the memory that's returned by this allocation function by the slab allocator. You know, likewise, you can call a shortcut, which looks a lot like kzalloc, right? You know, we have kmalloc and we have kzalloc, right? And so this is kmemcache zalloc, right? This is just saying, hey, you know, this just basically automatically does this for you. If you look at kzalloc, you'll see that it basically just, you know, calls this thing here, but it passes in your flags and tacks on this 0 flag for you so that you don't have to do it. It's a very fancy function, right? If you take a look at it, it just ORs in that flag for you. So this will also zero out the memory returned by the allocator. And so, you know, again, we have an idea now of what this slab allocator is, right? You allocate, it will allocate, you know, some blocks of memory from the buddy binary allocator, the binary buddy allocator, and it will, you know, you will register with it the type of object or the size of the object that you want to pack into these frames, and then this thing will start packing objects into frames for you. And so this is really, really nice. This solves the internal fragmentation problem, right? And there are a couple implementations of this. There are several ways to do this. And this is where the naming gets confusing. So this is the Slab Allocator, right? This is the Slab Allocator. It does that thing that we were just talking about, right? There are 3 main implementations that do this in slightly different ways, but the result is always the same. The oldest one is called the Slab Allocator. This is like the original KNR allocator. It's very compact. It packs these objects in there very, very tightly, right? But it's not very efficient, right? Or it's not very performant, rather. You might only see this now on embedded systems because it's very efficient in terms of how it utilizes the memory. It's not very wasteful. It's very compact. It's a compact allocator. It compacts these objects into page frames very nicely, but it's not necessarily fast. So again, you'll see this on embedded systems. SLAB, or the slab, and this is where things get confusing, right? Because this thing is the slab allocator, but there's also the slab allocator implementation, or the SLAB. People tend to say it out loud like SLAB, or people will say, or people will write it in all capital letters to imply that it's the SLAB implementation, right? And this is the Solaris, old Solaris implementation. It's very performant. It's very cache efficient, but it has problems. It's very, very, very memory wasteful. It tries to do things like keep everything cache hot. It tries to keep all of the slabs and objects allocated in the slabs cache, hot in the cache. And so it's constantly doing things like checking to see, if the items are hot or not. And it's constantly doing updates and swapping out all these queues. And so in reality, it uses a lot more memory. It's the opposite of SLOB, basically, which is very compact memory representation. It's very not compact. It wastes a lot of memory, and it also can waste a lot of CPU cycles if you start stacking up these crazy supercomputer systems that have lots and lots of cores. It has trouble keeping track of all of the different memory efficiencies or cache hotnesses of all the different queues. The last one is SLUB. SLUB is the newest one. It's the one that's currently the default. It's the one that we're going to talk about today. It was written by a simply brilliant man named Christoph Lemmer, who is a German computer scientist. He, worked for Silicon Graphics at some point in time, and he was doing some supercomputing things for NASA at one point. And he had these large multi-node supercomputers that were running SLAB, and he was having serious problems with it. So he just sat down and rewrote the allocator, and he called it SLUB. And it's very, very nice. It's been around since about 2011, and it's now the default, right? And that's what we're going to talk about today. And it's very, very nice because it has lots of nice, not only is it very efficient, as we'll see, in terms of memory usage and things like this and performance, but it also has some very nice integrated debugging facilities that will make your lives much easier as you're trying to debug your kernel modules. But first we have to understand how it works. So let's see how SLUB works at a very high level. So again, the naming gets confusing because this is the slab allocator, right? This is the SLAB algorithm, and this thing here that we're going to pack our objects into is called a slab. So, when people are talking about a slab, are they talking about the allocator? Are they talking about a slab of memory that you're going to cut up into chunks and give, back to kernel space? Or are they talking about just the general allocator? So just don't get confused by this. This is the slab allocator. Its job, regardless of how it does it, is to take blocks of memory returned by the buddy allocator and to cut it into small pieces, right? That we return to kernel space. The SLAB is an algorithm that we don't really run anymore. And this is a slab, which is a couple blocks of memory, a couple page frames returned by the binary buddy allocator. And this is what we're going to be cutting up into our objects, right? And so this is a free slab, right? And we know, right, because we looked at this just a second ago, right? We're going to be cutting up this slab into all these equally sized chunks, right? The only thing we're going to allocate out of the slab are struct things, and all struct things are the same size, right? And so this is the idea. When we allocate a slab, we know the objects that are going to go in it, right? Only one type of object is going to go into the slab. And so we can mark off regions we know how big each one is. And we know that this region is going to eventually at some point occupy an object. This one will eventually occupy an object. So will this one, so will this one. These are all free right now. But we know exactly where the objects will live within this slab. And so what we do, and this is where the, architecture is very smart, right? Is it will use this free space to actually store the data structures necessary to manage the slab, right? This is the clever part, okay? So before we look at this, right, let's back up. This is a kmem cache, right? This is a kmem cache struct, right? This kmem cache struct right here, right? This is our mem cache that we created. And we said, hey, create a new mem cache that's designed to store struct things, right? That's what this said here, right? We created a new mem cache. We put its pointer in here into thing cache. We created a new kmem cache, right? And so this is a kmem cache. And it has a lot more members than this, right? Again, slab allocator is very, very complicated. I'm just trying to give you an idea of how it works, of how slub works. So it has a name, obviously, right? Which we can see from user space. That's that string that got passed in the beginning here, way back in the day, right? This is its name, right? And we'll see that in a minute, how we can see this from user space. It keeps track of two lists, right? Or two things. It keeps track of the CPU slab. This is the currently active slab. Every CPU manages its own active slab, right? And by keeping the active slab, by keeping a separate active slab for each CPU, we don't have to worry about locking, right? We don't have to lock this. There's no lock, right? We don't have to worry about some other CPU coming in and trying to allocate something in the slab while we're working on it, right? It's independent. It's, every CPU has their own working slab that they're currently doing allocations on. So this makes it much more efficient. We also have this node pointer in your kmem cache structure that keeps track of all of the slabs for the node, right? And we looked at what a node was last time, right? This is a single processor that has multiple cores, right? So, each core basically will have its own kmem cache CPU, like a personalized slab that it's doing allocations from, but the entire node will also be able to share slabs in these lists, this partial and full list, right? So that they can be visible to other cores. And this does require locking. So, ideally, we'd like to only do allocations and frees within, the current CPU's working slab. But, occasionally, we'll have allocations and frees between CPUs, and we'll have to, go down to this other list here. These other lists of slabs down here that we'll build in a minute that are shared between all the cores on the current processor. And so, of course, this requires locking. And so how do we do this, right? Again, these are all free. We know that they're not being used, but we know their size. And so we store data structures in there. We store data structures in there that are used to manage all of the free areas, right? So this thing here, the currently active slab for the CPU, right, has a free list and a pointer to a page, right? This page pointer points to the beginning of the page that forms the slab, right? The slab, again, could be multiple pages, right? You're asking the binary buddy allocator either for an order 0 allocation, order 1 allocation, order 2 allocation. So the slab, the first page of this slab, right, is pointed to by this thing here, right? But it could be multiple pages depending upon how big your objects are. You might need more than one page just to store a single object, right? But this is the idea. Let's just assume it's one page at the moment. Okay, so this free list thing here, what it does is it points to the first free object in this slab. And each free object contains a data structure, right? And it consists of a pointer to the next free page or to the next free object. This is the free pointer, right? So the free list, right, points to the first free object location in the slab. And if we follow that, right, stored in this free area is the pointer to the next free area in the slab. And if we look at that, we'll find a pointer to the next free area in the slab. And if they're all free, all of the free areas, will point, they just continue pointing, right, until we find the last one. And the last one will point to null. So it's a singly linked list, right? That's embedded in this slab, right? And of course, the padding is there to keep these things aligned. And this poison we'll talk about later. This poison is something that can be inserted that you can use to see if somebody is reading from a free area. In other words, you shouldn't be doing that, obviously. Like, nobody should be reading from these. And if somebody writes into this for some reason, which you obviously shouldn't be doing, then we'll notice because we've put poison data values in here. They shouldn't change, right? And if you read some memory, right, and you see the poison values, then you know that you somehow got the address of one of these things that you shouldn't have. You shouldn't have an address of a free kmem-cache area unless it's been allocated to you, in which case the poison will be freed. So we'll see how this looks, right? Let's say that somebody calls me kmem-cache alloc and tries to allocate, a struct thing. What will happen is this free list pointer will get updated, right? We'll look at what the current free area points to. It's this free area here. So this is the next free area. So we update the free list to point to the next free area. And then we take this thing here. We either zero it out if kmem-cache alloc was past the zero flag, right? Then we'll zero this payload out. If it has a constructor, then we'll apply the constructor. Otherwise, we just return this thing, right? And this is the allocation that gets returned to the user. And so they can use this now. This is a struct thing, and its address gets returned to them. And it's their job to keep track of that address. We don't keep track of this address anymore, right? It's not part of our list. We're not tracking it, right? It's the responsibility of the caller to keep track of their memory. And so this is why dynamic memory allocation, the memory leaks are a problem. Right? The allocator is not keeping track of the addresses of dynamic memory that it's given out, right? Directly, at least, right? It's your job as the caller to keep track of that memory address. And when you're done with it, you pass that memory address back to the allocator, and it will find what slab it lives in and restore this to being free and update these pointers, right? Good. So now the free list points to the next free allocation, and this one's currently being held by some caller. And so let's say this one gets allocated. Somebody else comes and says, hey, I want to allocate a struct thing, right? So the address of the next free one gets returned to the caller, right? The caller now has to manage the address of this block, and the free list is updated to point to the next free area. So hopefully you can see how this is very, straightforward, right? Up to this point. We can alloc another one, right? And then let's say that this one gets freed, right? The person that alloced this struct thing, they called kmem-cache alloc on this, to get a struct thing, returns this thing, right? They free it. They call kmem-cache free. They free their thing, and it comes back, right? We look up what cache, what slab it should go into, and we free it, right? Because the user passes in the addresses of things that they want to free. So this becomes free, right? And then we have to update these free list pointers, right? So we know the address of this thing, the user just passed it in, right? So what we do is we take the free list, right? We keep track of the current, the next free item over here, right? And we store this address into here. So that makes this thing point to this free object over here. And then we update the free list pointer to point to the beginning, the address that was just returned to us, right? Remember, the address of this thing was passed to us when we called free, right? When free was called, free passes the address of this allocation back to us, so now we can hook it back into this block. So this is good. So hopefully you see how this works, right? They don't have to be continuous. We have this, singly linked list. We keep track of the list head here, and we can just use it to find the next free allocation. And we'll know when this slab is exhausted because the free list will contain null. The free list will point to null, and we'll know that this slab is full. And we'll have to ask the binary buddy allocator for another one. And so that will eventually happen, right? After many, many, many allocations later, we'll have a situation that looks like this, right? What will happen, right, is the application or the kernel, some kernel process, right, has allocated a bunch of these struct things and filled up entire slabs, right? And when entire slabs get filled up, right, they get moved, right? There's only one active CPU slab. When the slab gets full, when we see that that free list points to the null pointer, what we do is we take that slab and we move it to the node, one of the node lists, right? We move it to the full list, right? We move it to the full list. And this is a doubly linked list of these slabs. and it keeps track of all of the slabs that are full. Okay. And so hopefully you see how this works. And so when one of these fills up, we move it, we obtain the lock for this doubly linked list, we link it into this full list. This is a list of all the full slabs, and we ask the binary buddy allocator for another slab, right? And then we start working on that one. And as you can see, since we did that, several allocations have come in and we've satisfied them. And now the free list points to this last free item here. We have one more left, right? So hopefully you can see how this works, right? Now, what's going to happen is eventually, right, the part of the kernel that allocated this struct thing here is going to free it. And that's okay, right? When that address is returned to us, when free is called and that address is passed in, we'll find the slab, we'll go through this list, right? We'll find the slab that contains that address, and then we'll free this area, we'll free it, right? These dotted arrows indicate that there's a data structure here that I'm not showing you, right? There's actually a struct page data structure here that embeds this list head that does this doubly linked list stuff and also points to each one of these slabs and also points to the free area, the beginning of the first free area on each slab, right? And so, fine, one of these full slabs is no longer full, right? The struct thing was returned to us. The block of memory that held that struct thing was returned to us. So we free it and we keep track of where it's free now. And look at what we do. We take this slab and we remove it from the full list, right? And we move it to the partial list. So this is a partially used slab. This is a partially used slab. And again, all of the cores on the CPU can see. These are nodes. These are node-based lists. So all of the cores on the CPU can see these lists, right? And so this is like a pool. You could think of the partial list as a pool of slabs, right? That the different CPUs can swap in for being their active slab to do allocations from when their current slab fills up, right? So if there are partial slabs here that we can swap in, when this slab up here gets exhausted, we don't have to ask the binary buddy allocator for a new one. We can just, swap in one of our partial slabs and start using that one, right? So you have this cycling going on. At some point, you'll get some sort of steady state number of slabs, right, that you need to satisfy the system, and you'll just kind of be cycling between them, and you won't have to continue to allocate new binary buddy blocks. So let's say that this one here gets freed too, right? This item here, let's say somebody calls kmcache free and frees this struct thing, right? So this one gets freed. And so, this area becomes free. We can now satisfy a kmcache alloc request using this slab. And so this slab is now only partially used. So we add it to the partial list. And so we have two slabs in the partial list, right, that we can use later if this one gets full, right, which will happen just a second. And then let's say that this item gets freed too. So this item gets freed as well. And so this free list gets updated. And so you can see, right, how this is the game. It's a fairly straightforward game, right? It's just a linked list of free objects in these slabs. We have an active slab for each CPU, and then we have these shared slabs between all the CPUs. And as their active slabs become full, we'll see, hey, is there a partial slab I can swap in, right? And you'll do that if you can. If not, you'll ask the binary buddy allocator for a new one, and you'll add a new slab to the system, and they'll keep cycling like this. So eventually, this last allocation will happen in the active slab. So this slab will be full. We'll move it down, right, to the full list like this. And then we'll say, hey, I need an active slab, right? Do I need to ask the binary buddy allocator for a new one? And you say, no, I can look at the partial list here and see that the partial list has slabs in it. So I'll find a slab in the partial list and I'll move it to being the active slab for the CPU, right? And so now, again, this is that cycling I was talking about. At some point, right, you'll have asked for all of the slabs that you need to maintain some sort of steady state situation where you're just cycling out these slabs as memory requests come in and out. As slabs become completely completely empty, you can either choose to return them to the system or you can hang on to them, right? And so as the memory pressure on the system increases, right, as user space needs more and more memory, you can start returning memory to user space. But if it doesn't need that memory, then you can just keep these caches active and increase the system performance. And so this is how it looks, right? And then of course, as more kmem cache alloc requests come in, you would satisfy them by taking from these areas here, right? And then you keep cycling. And so this is the basic idea. Of course, there's lots of stuff that goes on, like with NUMA, multi CPU systems and all sorts of caching stuff. I mean, the implementation is about 6,000 lines, which isn't massive, but it's big enough that I can't, we could really just dig in. You could become a slub expert if you wanted, SLUB expert, and read all 6,000 of these lines and know exactly how it worked. But this is the basic idea. This is what's happening. And so, we have some idea, right, of what's happening now. Right, when you want memory for kernel space, right, when you say, hey, I need to allocate a struct thing, right, or the CPU, some part of the kernel says I need to create a new directory entry, or I need to create a new process, these are all structs that have known size that we're used to allocating lots and lots of, so they each have their own slab cache, right? And so we're constantly asking the slab allocator to allocate these structs for us in kernel space. Most kernel structs come from the slab allocator, right? And it's very efficient, because the memory for these structs is already allocated. We just return the address, right? That's all we have to do. We don't have to ask the binary buddy allocator for it. We don't have to allocate new slabs or anything like this. We just return this address. It's already allocated. It's being held in this slab cache. So these memory addresses for these structs are cached, right? They're already allocated. We just return their address and mark them as not being used, not being available, because somebody's already allocated it. Somebody's using it. Right, so this lives on top of the binary buddy allocator. This is the slub implementation, which is the common one now. And so, of course, as you can see, on top of this, the interface is kmem cache alloc, right, which is what we were using in that example to allocate struct things. And again, this is happening all the time. This is happening all the time with all of the various commonly used structures. And of course, this is fast, and it's necessary that this is very fast, because, for example, if you're doing network communication, you have to constantly allocate structures for TCP/IP packets, right? You need to be able to allocate those TCP/IP packet structures very quickly, and the slab allocator allows you to do that. The packets are effectively pre-allocated, right? You just get the address of one. Slab allocator gives it to you, and it keeps these caches so that they're readily available at any time. And because these are per CPU, there's no locking required in order to modify this. This is very, very fast. So, good. We kind of have an idea of what's going on. And again, you can see these caches from user space. They each have a name, that's string, right? And so if you're in user space and you're the root user, you can only do this if you're a root user. So you can use sudo, or you can, log in as root, whatever you want to do. But you can say, hey, read this file in proc. Again, proc is a pseudo file system, right? It generally contains information about all the processes on the system. But you can read the slab info file, and it will tell you about all the slabs that are currently active in the kernel. Right, it's a pretty long list. It's not as long as you would think it would be. It's actually relatively short, given the idea that it's all of the caches on the system. But you'll see this big list. Like these are file pointer structs. These inode caches, these represent files on disk, right? D entry represents a directory. Task struct represents a process. We'll look at this next week when we look at the scheduler. Right, a task struct is the structure that represents a process. It holds the process ID number, it holds the group ID number, it holds a pointer to the memory map, it holds the pointer to the file descriptor table. A task struct is effectively a process, right? And so it would make sense that we would need to allocate those structures very quickly. And so we have a kmem cache for them. We have a slab cache for them, right? And it goes on, right? Signal cache, files cache, mount cache, all these great things, file user space, file system and user space, file cache, all this sort of great stuff, right? And you can see, how many active objects there are and how many objects are available, right? So num objects, right, is the number of all objects, right? Ones that are allocated across all of these slab caches for this, all of these slabs rather for this particular slab cache. Right? If you were to count, all the allocated ones and all of the unallocated ones across all of the slabs that are being managed by the particular slab cache, then you get this number here. This is the number of objects that this particular slab cache here named, file pointer or FILP is currently holding, right? These are the number of cached objects. This is the number that are currently allocated. This is the number of currently active objects, right? So you can see there's quite a few of them. This is the size of an individual object in bytes. So these particular structs, this is a struct FILP. This is a struct D entry. This is a struct task struct. You can see how big each one of these things is, right? FILPs are 256 bytes, right? Task structs, the structure that represents a process, is nearly 2 pages in size, right? It's 8 kilobytes, right? And so you can see, how many objects there are per slab, how many can you fit into a slab, and how many pages make up a slab for that particular slab cache. And so, in this previous example, I said, let's assume that these slabs are small because these objects are small, but you can absolutely create slab caches for very, very large structs, like task struct here. Task struct is quite large, right? It's about 8 kilobytes. And so each slab managed by this slab cache is 8 pages. Right, is 8 pages, right? And so you can only fit 4 objects in a slab, right? Other things like directory entries, right, are very small. They're only 192 bytes, right? So there's only 1 page. We only ask the binary buddy allocator for 1 page when we allocate a new slab for this particular cache. And because each object is 192 bytes and each slab is just 1 page, which is 4096 bytes, we can fit 21 objects in 1 slab. And you can see that we have quite a few of these. We have a lot of directories. So hopefully you can see how this works, right? You can really get some insight into your system by looking at how the various slab caches are being utilized. You can see that the system probably has quite a few files, right? It has many different file systems that are being used. So now that we know about slab caches, to some extent at least, we can talk about kmalloc for real. Up until this point, we've been saying, hey, kmalloc is malloc for the kernel. And this is not entirely true. Kmalloc is actually looks something like this. Kmalloc manages internally an array of slab caches. Right? And that's what this is trying to say, right? This is an array called kmalloc caches that's held internally by kmalloc, the kmalloc subsystem. And every element in this array is a pointer to a kmem cache, right? And so that's what I'm trying to draw here, right? This is one of those kmem cache systems. And the first element in this array holds the pointer for the kmem cache system that handles allocations that are only 8 bytes in size. You also have a kmem cache system that's for allocations that are only 16 bytes in size. And you have another one that's for only 32 bytes in size, right? And 64 bytes in size, all the way up to 1 kilobyte in size, 2 kilobytes, 4 kilobytes, 8 kilobytes in size, right? So hopefully you see how this works. When you say, hey, I want to allocate, some memory using kmalloc, and you say, I want, 50 bytes, right? Kmalloc looks through this list and says, oh, well, you want 50 bytes. Well, I can't fit that in an 8-byte slab object. I can't fit it in a 16-byte slab object or a 32 slab object, but I can fit your 50 bytes into a 64-byte slab object. And so I'll put it in the 64-byte slab cache. And then you'll get a block of 64 bytes from the 64-byte slab cache to satisfy your 50-byte request, right? And you can see this, right? Again, if you look at slab info inside of proc, you'll see, in addition to all of this stuff that we just saw, all these very specific non-generic slab caches, you'll also see these generic slab caches that kmalloc keeps. And they all are named appropriately, right? You can see that this is the 8-byte slab cache for kmalloc. This is the 512-byte slab cache for kmalloc. And you can see, how many objects it's currently caching. It has in reserve, right? You can see how many of them are currently used. You can see the object size, which, obviously matches the the name, right? So you have an idea of, obviously these slab cache objects match the size of the kmalloc cache name. Otherwise these would be named rather poorly. You can see how many objects you can fit into a slab, and you can see how many pages are required to maintain 1 slab in one of these caches, right? And so it makes sense that if you have a slab cache that only manages 8-byte allocations, that it would only require 1 page for a slab. And you could fit 512 objects, 512 8-byte objects into that 1 slab, right? And you might say, well, that's silly, really? 8-byte malloc, right? And you say, well, yeah, look, it's actually perfectly being utilized, right? It has, at this moment, around 13,824 objects available, and every single one of them is being used perfectly, right? So the slub algorithm is very optimized. It's very good at only keeping the number of objects in the cache that it actually needs. The cache utilization is very high most of the time, close to like 98%. And so hopefully you can see how this works, right? And so these are generic blocks of memory. These are chosen somewhat heuristically for common allocation sizes, and you can see they pretty much hit it on the nose. They all have very good utilization, and they're all being used. We don't have any one of these that has 0 objects in it. So this is good. And so again, the way that this works, if you call kmalloc and you say, hey, I want 5 bytes of memory, you know, and it can just be a general allocation. This flag doesn't really matter, right? This is just going to say, you know, can you go to sleep when doing this, right? If this is atomic, then you can't. And basically, if you say, hey, I want 5 bytes, well, kmalloc is going to say, hey, you know, will this fit in an 8 byte block slab object, right? And you'll say, yeah. And so it'll give you, you know, a slab object from the 8 byte slab cache, right? You'll get one of these, right? And so you'll add to this list. Right, if you say, hey, I want a kmalloc 72 bytes, well, you know, that's too big to fit into a 64 byte object from the 64 byte slab cache, so it'll get put into the 96 byte slab cache, right? And so on, right? If you ask for 2600 bytes, well, you'll get put in the, this is a mistake. You'll get put in the 4 byte slab cache, right? Because this, I don't know why I did this. The 2 kilobyte slab cache obviously is incorrect, right? 2 kilobyte slab cache object size is 2048 bytes, so 2600 wouldn't fit in there. So it would have to be upgraded to the 4 kilobyte slab cache. So it would actually go here. Right, so hopefully you see how this works. We just have an array of these slab caches and we choose the correct one based on the amount of memory that's requested through kmalloc. So you're not getting exactly the amount of memory that you requested. Now I want to talk about this, right? Because you're not getting the exact memory that you requested, right? And also we say, right, in the C standard, you know, if you write outside of the extent of this array, if you ask for 2600 bytes and you write beyond that, we just say that undefined behavior happens. We say bad things happen, right? That's what undefined behavior means. It means we don't know what's going to happen, but bad things are going to happen, don't do it. And the reason for why you don't do it is really irrelevant, right? The standard says not to do it, so don't do it. And so the people that are designing the implementations that back these allocations are depending upon the fact that you won't do it. And they also don't have to worry about what they do in response to that if you break that rule. They say, if you break that rule, we can do whatever we want. So they don't have to worry about it. If you're in user space, generally your application will segfault if you write beyond the extent of a dynamic allocation. You might even corrupt the heap. And in this case, you'll corrupt the slab cache. And so we'll see what happens when you corrupt the slab cache. So let's say that you dynamically allocate 500 bytes of memory using kmalloc. Right? And so this will go, right? This 500 byte allocation will probably get placed into the 512 byte kmalloc slab cache, right? Because it will fit there. And you get a pointer to one of those objects in the slab cache. And then let's say that you do a stir copy on it. And you try to stir copy into this block of memory, into this object that lives in the 512 kmalloc slab cache, an unterminated string. Right, and as you know, the way that stir copy works is it will continue to copy bytes starting at this memory address until you reach the null character. If your null character is missing, then stir copy will go on until it finds some byte in memory that just happens to be equal to 0. And so this could be quite bad. If this is not null terminated, if you don't run into a 0 byte by pure luck before you get to 500, then this will be undefined behavior and you don't know what's going to happen. So bad things will happen to you. And again, in user space, your process would just segfault. If you're in kernel space, then it's much worse. And so let's look at what happens. So when you kmalloc 500 bytes, you're pulling an object from the kmalloc 512 slab cache, right? And so one of these free objects here is going to get returned. And let's say that before our kernel module does this, let's say that some other system call also just happened to kmalloc, you know, some memory that fits within a 512 byte slab cache object, right? And that's the thing about kmalloc is that all of these 512 slab cache objects, all of these 96 byte slab cache objects, these are all shared between all parts of the kernel, right? So at some point, some system call maybe allocated kmalloc something and they get this address here. Right, and then let's say a little bit later, you know, the kernel gets preempted, your module runs, and you kmalloc 500 bytes, and you get this one right here, right? And so hopefully you can see what's happening. These are right next to each other. So you have the starting memory of this address here. The payload is where you put your data, right? This is where you're going to be stir copying stuff into, right? This is the destination address. This is the memory that was returned to you. This red zone here is satisfying the requirements of the pad, right? This is for alignment purposes, but it's called a red zone because we're smart about what we pad it with. We put known values in here. And if you if these values ever change, then we know that somebody has written past the end of the slab object. And we know that some process is misbehaving, and we can use this to try and figure out who did it. And so this is the debugging functionality that I'll talk about in a little bit. Same thing is true with the poison, right? If the poison bytes change in a free block, then we know that somebody's messing with blocks that they don't actually have, that they don't actually own. Right, so this is again helpful for debugging. I'll show you how to do this in a little bit. So let's say, some system call malloc this block here, kernel gets preempted, your kernel module runs allocs this block here. Starts doing this string copy here. And what happens is it doesn't find the null character in the source string and just continues to copy stuff into this buffer, into this dest block, runs past the 500 block allocation, blows through the red zone, blows through this entire block here, returned by this other system call, runs through its red zone, and then ends up finding a null character in the source string, right? Somewhere like, this would be roughly what, 1200 bytes in. And so this destination buffer has been just hosed, right? You've just gone way outside the 500 bytes that you allocated into this next allocation that was returned to a different part of the kernel, even past that into this free block here, right? And that's where you stopped. And when you did this, you did several bad things, right? Because look at how these pointers are set up. This free list points to the first free block, but this first free block here currently contains a pointer to the next free block after it. This is how we find the next free block after we do this allocation. And so when you blow through memory like this, you do this undefined behavior thing. Look at what you did. You totally broke this pointer, right? You wrote some data into this FP field, right? Whatever data you wrote past or beyond, I mean, who knows what it is, right? You wrote some arbitrary number in here. So this is really, really bad, right? And so the data that was stored in this kmalloc allocation by this other system call is now corrupted. So this is really bad. Who knows what's going to happen when control returns to the system call that's using this memory? Who knows? The payload is now totally overwritten by whatever your process wrote in here. It wasn't supposed to go beyond 500, and it did. And then, right, it continues to blow through and mess with this free pointer. And so now this free pointer contains some random address. It's just whatever bytes you happen to write to that memory location when you went past the end of your allocation. So now this pointer chain is broken, right? This list of free pointers is broken. And so now kmallocs of this size will fail as long as we're operating on this slab, right? Because maybe you'll be able to successfully allocate this thing to something, right? Because you can still find it, right? But then the free list pointer will get updated to point to whatever this is. And we can't return blocks of free memory from this area. Who knows, right, what this is? So this is bad. Kmalloc's pretty much broken, at least for K512 allocations. And so, this is a screenshot that somebody posted to Piazza, and it's hard to explain these things. But now that you know a little bit about how the K-Memcache system works and how kmalloc is built on top of it, we can kind of see what's happening here, right? So some stuff happened, right? Some VIC stuff happened. And it says, hey, a general protection fault happened. We're trying to access this weird non-canonical address. And the instruction pointer is currently inside of kmalloc, right? And if we look, right, we'll see that the return address, right, RAX generally holds return values. And so kmalloc, or something that is internally used by kmalloc, probably one of the slab cache functions, returned an address that's invalid. That's what non-canonical means. So somehow one part of the slab allocator returned an address to a slab object that's invalid. And then kmalloc, after it received that, tried to dereference it in some way, and we got a seg fault, right? And that non-canonical address was probably returned because this happened right here. one of these free pointers got overwritten. And so, what does non-canonical address mean? We looked at what the virtual address space looks like in 32-bit Intel x86. In 64-bit x86, it looks something like this. The 64-bit address space is so massively huge that we couldn't possibly populate all of it with physical memory. It would cost too much money. And so what we end up doing is using this small address range down here to map the user space. And we use this equally sized small address range at the top to map kernel space. They can each map about 128 terabytes of memory each. Between the two of them, they can map 256 terabytes. And they're not using close to the full virtual address space. And so as a result, there's this vast region of unused virtual addresses in the middle of the 64-bit virtual address space called the non-canonical space. And this basically means we don't use these. If you ever encounter a virtual address that's between this address here and this address here, then you know that it's invalid because we never map these. We never map these. And so, if you happen to dereference a pointer, that contains one of these addresses, it means that something has gone very, very wrong, right? And so if kmalloc is returning addresses like this that fall in the non-canonical range, chances are it's because of this. This free pointer here got corrupted. And so the slab cache tried to return the address of the next thing in the free list, but it wasn't actually the address of a free object. It was the address of it was something that you blew into the address field when you overrode a slab object. Right? And so as a result, bizarre things start happening, right? Later, you'll see that this seemingly unrelated, clone, it's saying, hey, we're doing some syscall here. We're going to do a clone syscall. Clone is the system call that fork wraps around. When you do a fork system call, you're actually calling clone on Linux. So this fork system call starts failing. It doesn't seem like fork should be failing because we didn't do anything with fork. It looks like something's bad. So we're trying to create some process in user space, and it's not being created because the system can't fork a process anymore. And if we go up, we'll see that the system can't fork a process anymore because one of these things that it calls in the process of forking, and namely it's trying to prepare security credentials for the process, make sure that it can't access files that it can't access and all this sort of great stuff. When it does this, if we look, this question mark means somewhere around here. Kernel's not exactly sure about this address, but it's somewhere around here that things started going bad. And so if we look at this, we find this function in the kernel, we see it's this thing here. And you see the first thing that this thing does is it calls cred alloc, right? It's trying to allocate some credentials, right? It's trying to get a new credential structure. And so you can see like, hey, maybe we look at this, and if you find it, you'll see, yeah, it's trying to kz-alloc something. And it's probably trying to kz-alloc something that's on the same size that would fall into the same kmalloc slab cache as the allocation that your kernel module performed and did an out of bounds write on. And so you can see how, kmallocing something in one part of the kernel and doing an overrunning that buffer, writing into adjacent slab objects can corrupt the operation of other parts of the kernel because they're all taking from area in the same memory. Taking memory from the same area. All of these objects are adjacent to each other because the way that they get packed into slabs. And so this is bad news. You really have to watch out for this, right? You have to be very careful about accidentally going past the extent of a buffer. If you go past the extent of a buffer, dynamic allocation, then it's possible that you'll blow through the padding and that you'll hit adjacent objects, which is very bad. And even worse, you might break some of the internal data structures that are being used to manage the dynamic memory allocator. And if you break the dynamic memory allocator's data structures, the dynamic memory allocator doesn't work anymore, and very bad things happen, right? So you have to be careful. This is bad news. So now, we have a little bit more insight, right? We know how kmemcache alloc works, right? We can get, very specific objects. We can create memcaches for specific structures that are commonly allocated and commonly deallocated in order to increase system performance. But we also can create generic slab caches of commonly used sizes. And this is what kmalloc does, right? It's got the 8-byte cache, the 16-byte cache, right? And of course, you can see how this can also create problems because when you kmalloc something, you're sort of sharing slab caches with other parts of the kernel. I mean, you're obviously doing that as well if you're, dynamically allocating directory entries. There's some other part of the kernel that also dynamically allocates directory entries. But, kmalloc objects, a lot of you don't know who's going to be dynamically allocating these things. So you have to be careful. If somebody goes past the end of their dynamic allocation from a kmalloc, it's possible that they could accidentally hit your data. If you go past one of yours, you could hit their data, or you could corrupt the entire system, the entire allocator system for that bin size. So you have to be careful. And now the question is, well, if this is the situation, right? If kmalloc is really just looking at this array of kmem caches, of slab caches, right? And it can do slab caches of, allocate objects from these various size slab caches. Well, does that mean that if the largest slab cache is 8 kilobytes, that the largest allocation that we can do is around 8 kilobytes? And, this could be the answer, but it's not. If you look at the kmalloc function, kmalloc internally, again, the theme with the way the kernel is structured is that external user-facing functions tend to wrap these double underscore functions that do the actual implementation. So this is how kmalloc actually works. This is the double underscore function that kmalloc wraps around. And if you look at it, you'll see, it gets a size and it gets the flags, right? This is get free pages kernel or get free pages atomic or whatever. And you'll see one of the first things it does is it checks to see if the size is larger than the largest kmalloc cache size, right? This unlikely thing is a compiler hint. This is telling the compiler to generate code that is optimal for a branch prediction that assumes that this is not true. So this is a hint. This is a hint that the fast path should be designed. So assuming that this is not true, this is not what will generally happen. So, if the size of the allocation is larger than the maximum cache size, in other words, if we try to allocate something bigger than 8,000 bytes, we pass control this thing called kmalloc large, and we pass in the size and the flags. And if you look up this thing, it basically works just like you'd expect, right? Kmalloc large takes the size and look at what it does. It tries to get the order, right? So you're going to pass in some size, and it's going to say, oh, you want 2 megs? What's the correct order for that? We're going to ask the buddy allocator. We're going to go down to the page frame allocator and get you some physically contiguous page frame memory. And the buddy allocator will satisfy your request. This order gets passed to kmalloc order trace, and it continues to go through and dip down into the binary buddy allocator and get you a contiguous block of memory from the buddy allocator of the order that will satisfy your size request. So it actually looks like this, right? So when you kmalloc something, you can get something from the slab allocator. If it's below 8 kilobytes, if it's above 8 kilobytes, then it goes to the frame allocator. It goes directly to the binary buddy allocator. And of course, these allocations will not necessarily be efficient because the larger these allocations get, the more wasteful these binary buddy allocator allocations become. And so, fine, right? Does that mean that if we can dig down to the binary buddy allocator in the event that our allocation doesn't fit within a kmem cache, kmalloc slab cache, right? Say that 5 times, right? And we dip down all the way to the frame allocator. Does this mean that the largest thing that we can kmalloc is an order 10 block? And the answer is yes. That means that this is the largest thing that you can kmalloc. So you can kmalloc things very quickly in a very performant fashion, as long as they're relatively small and can fit within the slab caches that are maintained by kmalloc internally. If you go beyond 8K, then your kmalloc will not be in a slab cache, and you'll have to dig down to the binary buddy allocator, and you'll get one of these orders. And this block, one of these 6 order blocks or 7 order blocks or 8 order blocks will be returned directly to you. So it'll be the same thing as calling get free pages. Right? And it also means that since the largest block that the buddy allocator can return is an order 10 block, this will be the biggest thing that you can kmalloc. So kmalloc always returns physically contiguous memory, whether it's in a portion of a slab or it's an entire slab, right? In other words, a block returned by the binary buddy allocator. All kmalloc allocations will always be physically contiguous, right? And this is the biggest one. if your system, right, has a max order of 11, then the biggest thing you can get is max order -1, which would be 10. And if your page size is 4 kilobytes, which it is on most systems, then that means that the largest allocation is probably 4 megs. If you need something larger than 4 megs, well, that's what vmalloc is for. Remember last time we talked about vmalloc and I said, you know, hey, this is for very large allocations, and I meant it, right? You generally won't be allocating more than 4 megabytes in the kernel. I mean, this is an insanely large amount of memory, right? And so if you need to go above 4 megabytes, or rather whatever page size times 2 to the 10 is, whatever your max order is for your system. Remember, I mean, a lot of the code that you guys may end up writing, if you do this sort of kernel work, is probably going to be in some sort of embedded system, right? And maybe you work for a company that embeds Linux in a smart TV or cable box or a smartphone or something like this, right? So these numbers can change, right? The max order can change, the page size can change. Just keep in mind this is what's happening, right? And so, you know, again, if you need to allocate a large, if you must have an allocation larger than whatever the buddy allocator can give you, that means you have to ask vmalloc. And it will start piecing together, right, individual pages returned by the buddy allocator and stitching them together to be virtually contiguous by setting up page tables, right? And that's why this is vmalloc, right? It's only contiguous in the virtual address space. The actual pages that back it are not physically contiguous, because they can't be. They can't be by definition. If you need something bigger than 4 megabytes, for example, an order 10 block, then it has to be, you know, some of these things stitched together. It has to be multiple pages stitched together that are not physically contiguous. And so again, this is why you'll see this being used to load kernel modules dynamically into the kernel, is because a kernel module can be quite large. It can be over 4 megabytes, right? And so you might need several page frames and stitch them together to map them into the kernel. And so their virtual addresses will be contiguous, but their physical addresses won't be, because it'll actually be backed by multiple page frames that are not next to each other in memory, because they can't be. The biggest you can do is 10. So hopefully that makes sense. And so, you know, with the time that we have remaining, I want to tell you, you know, how to debug these sort of things. And you might be saying, hey, is there anything we can do to detect this? I mean, clearly this is very, very bad. And we have these poison things here, and we have these red zone things here. I mean, they're clearly here for a reason. So how can we use them to try and figure out what went wrong when things go bad like this? And so the answer is, when you boot your kernel, you know, in the grub menu, you'll see that you can push the E key to edit the commands. And when they say that, you know, this basically means that you can change the grub config a little bit. And on one of these lines, you'll see a line that starts with Linux. And this is where the Linux kernel is getting booted. And these things that come after it, this line wraps around. That's why it's 2 lines. It's actually 1 line. It's just, you know, the editor here is wrapping it to 2. All the stuff that comes after Linux are the kernel parameters. These are the parameters that are being passed to the Linux kernel. These are basically command line parameters. It tells the kernel how to act. And so, you know, we're saying, hey, you know, this is the kernel that we want to boot. We're saying, hey, this is where the root file system lives. It has some, you know, UUID, right? And then, you know, we add slub debug to the end. And so this will put the slub allocator into debug mode. And this is very, very nice. When the slub allocator is in debug mode, when you write code like this, you say, hey, you know, I want a kmalloc 100 bytes, right? You know that this will come from the 128 kmalloc slab cache. And so if we memset this object from the slab cache with X characters, just this byte here, 300 times, we'll obviously be going past the end of the object in the slab cache, and we'll be hitting the red zone and maybe even an adjacent object. And so, you know, and then we free this thing. We'll see if this works, right? So if we load this kernel module, we know that this will segfault, right? Because we're corrupting the slab cache. We're just nuking this thing. We're going way past our object and running into adjacent objects in the slab cache. And so when we do this with slub debug enabled, you'll see this now in your kernel log, in addition to the stuff that you normally see. And this is really nice. The slub allocator will say, hey, there's a bug, you know, kmalloc 128 got tainted. Red zone was overwritten. And so the red zone is expected to contain the value CC, right? And so then it says, hey, it allocated, and it starts saying all this stuff, right? And it tells you, what it found. These are all of our X characters, right? X, hexadecimal 58. And then it will tell you a bunch of stuff, right? Hey, this thing here, this thing here, right? So it gives you a stack trace, and it will show you some of the red zones at different memory addresses, right? And it'll show you some object values at different memory addresses. And if you look at these things, you'll see, hey, look, this red zone here, red zones are supposed to contain CC. Well, this red zone here contains 58, it contains X's. So something went outside the red zone. Something went outside the red zone, right? And so this is helpful. This can help you to debug, what went wrong, right? Did you go outside the extent of an object that was dynamically allocated with kmalloc or kmemcache alloc? And you can say, yeah, some red zone objects are getting hit. I went too far, right? You can kind of see how far you went, right? And so we're talking about these red zones here, right? So if you go too fast, we wrote too many X's into our payload and we extended beyond it into the red zone. And the slub allocator recognized, and it didn't do this, the slub allocator didn't recognize this until free was called. Until free was called, right? Until free was called, kmemcache free was called, until this free call happened. So, this is the thing, is that slub debug isn't designed to babysit you necessarily. It's designed to help you find system problems. And so, it's still trying to be performant and still trying to run the system. So it's not going to check everything constantly, but it will check things when it's convenient for it and provide you with some useful information as it becomes available. And so it catches this particular overwrite into the red zone when the object is returned. When the object gets returned to the slub allocator, it will check the red zone and see at that point that it doesn't anymore contain what it's supposed to. And then it will issue this error when the block is returned to it. Right, so it's not like sitting there checking all the blocks constantly to see if people are being, no, it's not doing that. When you return the block to it, it expects the red zone to still be intact. And if it isn't, then it will yell at you, right? This makes sense, right? Because it shouldn't be reading these things while other parts of the kernel are using them. But once it's returned to it, it can read it and see, hey, has the red zone been modified? It shouldn't have been. I should have received this back with the red zone intact. And so if you read the comment, these comments are in, mm/slub.c, right? It tells you what the object layout is. And when it says object layout, it's talking about these things here, right? It's talking about these things here, these objects that live in the slab. And, it tells you, what poisoning uses, right? Things that are free have poison, right? It tells you what the value should be. It's 6B. The last byte of the poison free should be A5, right? This is poison end. So this way you can see, where the poison area ends. You can see this byte. If this A5 byte is missing, then you know that you're in trouble. Something weird happened. If you know that these 6B bytes aren't here in this poison area, you know that somebody's writing into a freed area. Maybe somebody did something like this, and these poison bytes got modified. Right? Likewise, they tell you, what the red zone value should be. Right? So red inactive is BB for inactive objects. And for active objects, it's CC, right? So that means that in these sort of objects here that are active, it's CC, right? And these sort of inactive objects, right? This pad, right, should be BB, right? So you can sort of look at the information that's returned by the slub debug, by the slub allocator when it's running in debug mode and get some sort of idea of what happened. Right? If it says anything at all, you know that basically you're probably either continuing to use some pointer after you freed it, right? Which would be a way that you could write into something like this. You call kfree, but then you continue to use the pointer. Well, you're going to keep writing into this memory here, and so the slub allocator will complain. If you write past, you blow away some red zone bytes, right? And then you call kfree and you return this block to the slub allocator. It checks the red zone to see if it's been tainted. It's going to complain to you. It's going to say something like this, right? And so, this is the last slide, right? Included in the kernel tree, there's a directory called tools. There's a directory called tools. And in there's a directory called VM, which stands for Virtual Memory Manager. And there's one file in there called slabinfo.c. And you can compile this thing. It's very easy to compile, right? You just, say GCC, compile this thing. and you can call the output file slab info. And slab info, helps you debug the slab allocator when it's running in debug mode. Even when it's not running in debug mode, you can get a lot of very interesting information. But if slub is running in debug mode, then you can use slab info to interrogate its status. And so you can force the slab allocator to validate all of its slabs at any time. Remember in the past, I said, hey, this thing's only going to notice if the red zone bytes got modified when you return the allocation to the slab allocator by calling kfree. Well, you can actually force the slab allocator to validate all of its slabs by calling this program as root and passing in the validate option. And it will force the slab allocator to validate all the slabs, right? And if it finds any problems, it'll print them to the kernel log like it did here. You can also look at slab caches that are being merged. If you have two structs that are the same size, right, that are of similar sizes, then the slab allocator can see that and say, hey, I can make the system more efficient by merging these two slab caches together, right? Because the objects are the same size, right? The caches will work exactly the same. And so they'll share slab caches. And so you can see which ones are being aliased, which is kind of interesting by looking at the aliases option. And then you can also view information about all slabs. This is like running proc slab info, reading this file here in proc that we looked at earlier, except it provides a little bit more nicely formatted information, a little bit more interesting stuff for you to look at, a little bit more insightful stuff. Again, you have to be root to do this. This actually just reads from sysfs. Right, all of this information that this thing is reading is being exposed through sysfs, right? It's a sysfs interface. And then, of course, you can see more options for the slab info tool, which is quite useful by passing in the help flag, and it will tell you all of the things that you can do with it. All right, and that's it. So hopefully this makes sense, and hopefully this is helpful, right? So when you're doing project 3, you can use slub debug, and you can use this slab info tool, and you'll have some insight into this business right here. You have to be very careful. There are lots of ways that this can happen, lots of mistakes that you can make. Again, using something after it's freed, or accidentally going over a buffer size or something like that. You can obviously corrupt the slab cache, and bad things happen. So congratulations, hopefully you're able to follow this stuff. Very few people actually know or are aware of how their memory is allocated. And it's obviously a good thing to know, right? How this whole system works, at least some idea of it. Lots of people just say, I don't know, I call kmalloc and like magic happens, right? But you can see how understanding, at least on some level, how these slabs are being managed and how the objects within them are being managed gives you a lot of very powerful insight in terms of your value in being able to debug these problems. Somebody says to you, hey, some bad stuff is happening, like this, what's going on, and actually being able to read it and say, hey, by looking at these crazy numbers, and all this sort of stuff, I can kind of divine the problem because I have an understanding of how the memory allocator works. Right, so this is very good. It's very helpful. Hopefully this is valuable. Okay, so that's it. So we're out of time. So I'm going to stop the recording. If you're watching on YouTube, thank you for taking the time to watch this video. Hopefully it was helpful, and hopefully it helps you in doing your project 3. And I will catch you next time. Have a good one.